Hello and welcome to this lecture. We're going to do something slightly different instead of just a regular lecture where we do just computations and derivations. We're going to do some computer simulation of probabilistic experiments. Now this is a bit different and also maybe a bit challenging to some of you if you have never seen a computer program before or something like that. But hopefully you've seen some computational thinking and you have some experience of looking at steps of numerical computation there, and you're also doing a Python course on the side. So hopefully these two together will help you get over this, and we are not going to use any major Python structure or anything like that. We're going to just use some simple thing, and most of the code I will give you. I mean, you have to just look at the code and learn how to run it. And we've also been talking about activities in this class, and this will sort of be part of your activity, and you'll see it's easy enough to do. I'll expect some very simple modifications maybe from you, and your instructors will help you in this as well. Okay, so let's get started. So like I said, one can define an experiment. An experiment is some sort of an action, isn't it? You do something and some outcome results, and one can presumably do that in a computer, right? So you can write a computer program that will simulate the experiment with maybe some realistic sort of conditions. So this is now possible, and what I will give you are simple Python routines for simulating experiments. And interestingly, from the simulations, using something called Monte Carlo simulations, this is a very standard technique today, you can verify, or you can actually by simulation find the probability of an event. Okay, so you have an experiment and you define an event and you do a computation to find what that probability of that event is. Turns out you can simulate it and verify whether these two agree. Okay, so that's something of, of very great interest to us, right? So you toss a coin. We've always been saying fair coin is 0.5, so maybe you should just have a way of verifying that actually has a meaning in real life, and that's something we will see later on, even in theory in this class. In practice also it's true. Okay, so this is this Monte Carlo simulation is very important in practice. A lot of quick experiments can be done like this. For complicated experiments you can actually do simulations and check whether your probabilities of events work out okay or not. Okay, so all this code will be available to you as a Python notebook in something called Google Colab, and these are things that are very important for you to learn in this program, right? Knowing a good Python notebook environment where you can go in and do some work is extremely important for a data science program. Today, if you get out with any sort of learning at all, you will need to be able to express or write some Python notebooks to explain your work, and this has become part and parcel of everything today, not just data science, even in other areas. This is very, very useful. So it's a good skill to have, and as part of this course you can take some first steps towards it, and as you go further in this program you will become more comfortable with using Python in a notebook in Google Colab or any other notebook environment that you like. Okay, so with that introduction, let's jump into this Python notebook. I've created a notebook for you in Google Colab, and I'll just show that to you, and it will also be shared to you. You'll have it available, and this is basically for simulating these experiments. So let's see that. So this is my Google Colab Python notebook, and you just have to go to this URL that you see here, colab.google.research.google.com, and this will be like a drive file for you. Okay, so you can use the online degree login that you have and go into colab.research, and you can create any notebook that you want, and this is a notebook that I've created like that. Okay, so any notebook will have cells, okay, what are called cells, and you can see the first cell is highlighted. I can go to the second cell, I can go to the third cell, I can go to cell after cell after cell. Everything is a cell. These blocks that you have here, this is a cell, and every cell can have either code or text. Okay, so you can see here code, text, and you can keep adding cells. Whenever you go here, you see plus code plus text, right? You can either add a text here, or you can add a code here. So for instance, like in the very beginning, if I want some text here, I can put it's in some language which is called Markdown. You can also learn that later if you like. This is so let me just call this probability in Python. So what I type here is in something called Markdown, and it's good for you to learn Markdown as well. So you can see some sort of a, title came here, and you can see this is probability in Python. So this is a way to type text. Okay, so you can see this is also a text column. I can edit it if I want to. If I don't want to, I can go back here, and then these are code. Okay, this is code. What you see like this are code. This slightly different background and foreground, that is code. This is all Python code. You can see Python code and text gets mixed up together. You write some text, describe something, and then you write Python code for doing that. Okay, so that's called a notebook. Okay, so notebooks are very nice. Any work that you do, you can see clearly that you can describe it in a notebook very conveniently. You write the text and then you write code. The code can be in many other languages as well. So Python is just convenient. In most cases, people use Python, but you can also have other languages. Okay. So now, so Google Colab, there is this connect. So Colab will connect to some virtual machine on the background. When you run the first command, it will do that connection on your own. You can see it's allocating and then it's connecting. And once it's connected, it will run this first piece of code. Okay, so it's connected, it's given me some RAM and disk, etc. And it has run this. Okay. So Python works with something called packages. You will learn these things later on, modules or packages, and I've imported an important module called NumPy, NUMPY as NP. So now this is, you need not really know the meaning of this, but let's go on and see how I'm doing this. So first I have a function for generating a uniform outcome. Okay, supposing you have n outcomes in the sample space and you want to select m outcomes independently, one after the other, uniformly. Okay, you need a function for that, and I'm defining that function. So you can run this. So your machine knows that this uniform nm is something that will generate uniformly. There are n outcomes in the sample space. It will generate m outcomes for you independently. Okay, so supposing, here's an example. Let's see an example here. Example is always good. Supposing you want to toss a coin, right? So there are two outcomes. I will denote the first outcome by heads. Number one, outcome number one is heads. Outcome number two is tails, right? 1 and 2. So if I could toss the coin once, I could toss it 10 times, I could toss it 100 times. So this is a command which prints one toss, okay, uniform of 2, 1. So now 2 is what? 2 tells me that there are two outcomes in the sample space. The first outcome is number 1, second outcome is number 2. That's what this 2 tells me. And I want one experiment to be done. Okay, experiment to be done once. What about this command here? Uniform 2, 10. Again, two outcomes are there, and I want to do the experiment 10 times. So toss the coin 10 times and tell me what happened. Here is toss the coin once again 2, that determines that it's a coin, right? So my outcomes are only 2 in number, 1 and 2. So and I want to toss it 100 times. So let's just see if I run this, what happens. So it tossed it first time. The first toss resulted in tails. The next 10 tosses resulted in so many 1s and so many 2s, and then the 100 tosses resulted in so many 1s and so many 2s. Once again, remember, 1 is my code for heads, 2 is my code for tails. Now it's easier to use 1 and 2 and things like that in computer programs as opposed to H and T. It's not very hard to do the translation, but this is easy enough. So let me just run it once again. Now I can run multiple times. You can keep running it and you see the outcome changes, right? When I tossed once, the outcome changed here. When I tossed 10 times, the outcome changed. It keeps changing. I can keep running. Every time I run, I will get different random outcomes. Okay, so this is what I meant by saying I'm simulating an experiment. The tossing of a coin is getting simulated here inside this Python language in some way. Okay, and you're getting the output here. Okay, hopefully that was clear. If you'll have this notebook with you, you can sort of hit this button here and keep getting multiple iterations going. The next thing I want to do is throw a die. We've been throwing a die calculations for so long, right? So here's throw a die. You could throw once, or you could throw 10 times, or you could throw 100 times. Exactly similar to before. Now notice all I've changed here is uniform 6, 1. Okay. So in a die, I know there are 6 possible outcomes. All of them are uniform. So all I need to do is make uniform 6, 1, and I have my die, right? So it's as good as that. So it's very simple. I can throw the die once, 10 times, 100 times, and off you go. There you go. You get the answer. And here the number is the same as the outcome, so I don't need to do any translation. So you see the outcomes here. So 1, 2, 3, 2, 1, 6, 6. That's possible. right? So you can run it different times you run, you get different outcomes. Okay, so that's throwing a die. All right, so simple experiments, you know how to do it. It's uniform outcomes is very easy. Okay, now the crucial thing we will learn is something called this Monte Carlo technique. This is estimating probability of events by simulation. I've given here a brief description of what it is. Okay, so the basic idea is this estimate. Okay, so I put equality here. It's probably not equality. So maybe I should say approximate here, just to get that right. Okay. So you can see here. So if you have an event A and you repeat the experiment n times independently, you keep on repeating it and simply count the number of times the event A occurred, which I could call as n sub A. Okay, and then if you take this ratio n sub A by n, you can show using various theory and also in practice you can sort of observe that this is a good approximation for probability of that event A. Okay, so this is the basis of Monte Carlo. Okay, so this equation right here, you repeat the experiment n times independently and count the number of times the event that you want occurred, NA, then NA by n is roughly the probability of that event A. Okay, so one can show also that as n becomes larger and larger and larger, this becomes a better and better and better approximation, and this is the method that's very useful. Okay, so we're going to just do very basic simulation here. The first simulation I'm going to do, we'll evaluate probability of a coin toss. Okay, so we know it's 0.5, right? I'm expecting my uniform to be uniform, so it's 0.5. So notice what I'm doing here, I'm counting. So this is where I count the number of heads. Okay, number of heads is 0, and for I in range, though this is basically like a repeating of a loop 1000 times. Every time I repeat this loop, I generate a coin toss and check if it is equal to heads. Okay, so that is the part which checks if the coin toss is equal to head. Okay, so maybe I can write that down here. Okay, so this is repeat coin toss, repeat 1000 times, whatever I choose to do, right? Okay, so then I count the number of heads and divide by 1000, I get a probability estimate by Monte Carlo. So let's run this. 0.492, 0.513, 0.48, 0.492, it's sort of close to 0.5, so you won't get the exact 0.5. What the theory tells you is as you keep going to 1000, 10,000, 100,000 and all that, this will become closer and closer and closer to 0.5. Of course, in computer simulations, there are so many other things to consider. But anyway, 0.5 is sort of what you have in your head in theory, and you got that in practice using Monte Carlo. So now this is a very, very nice result to have. So let's once again do probability of a die showing a number. Maybe you thought coin toss is too easy, so we can modify the Monte Carlo simulation. So what I would do for any Monte Carlo is copy this, paste it, and make it number instead of number of heads so that it's neutral enough, right? Number equal to 0, variable for storing the event occurrence. Okay, and then my repeat, how many ever times I want to repeat, and I do my experiment uniform of 6, 1, is it equal to 1? Okay, and then I do number equals number plus 1, and finally I print this, right? So I expect this number to be 1 by 6, so 0.157, 0.16 is pretty good. Okay, so maybe instead of just the number being 1, maybe I want to find the probability that the number is either 1 or 2. Okay, so what you can do is you can store the value of the die, okay, and then simply check if die equal to 1 or die equal to 3, then you increment. Okay, or okay, is that okay? So what will be this event here, die equal to 1 or die equal to 3? The event A is A equals 1, 3, isn't it? This is the event A. Okay, so probability of A should be 1 by 3, you should get something close to 0.33. Lo and behold, you got 0.333. I mean, how more exact can it be? I mean, that was just a fluke, I think. You do it once again, you get something else, slightly different. 0.321, 0.31, 0.355, slightly around 0.33. That's what you'll keep getting. Okay, So you see, you can make these small modifications, right? So you first do the experiment, okay? So you always have this for Monte Carlo, okay? This is repetitions. Then you do the experiment first, okay? Don't do anything more clever, just do the experiment and then event. That's it. So that's Monte Carlo for you. You can copy paste this to anything else you like, right? Variable for storing, repetitions, do the experiment, right? Have some logic for counting whether the event happened or not, and then increment the number, right? So this is the way to do it, right? So if you can change it, so I'm claiming that if you change this to 10,000, you will get something smaller. It will take a little longer to run. Okay, of course, I have to divide by the 10,000. Divide by 1,000, you'll get something wrong. So you see, you're getting much closer numbers, much more consistent, right? So 0.33, 0.33 is not changing. You're getting something much closer to 0.333, etc., etc. So these are things you can verify. Okay. So hopefully you saw this. So this is the essence of Monte Carlo. Okay. So you can always copy this and paste it somewhere, and then make the change that you want. Change your experiment, change your event condition. Okay. You got your Monte Carlo going. Just keep doing it, and you have Monte Carlo experiments. Okay. So this is the basic. Now let's consider slightly more complicated experiments. I'm going to consider 3 different experiments which are actually very classic probability experiments. We didn't consider the theory for it, so I've put a small description of the theory. Given your background in probability, now you will understand this. The first classic problem we'll look at is something called the birthday problem. Okay. So the birthday problem is a very interesting problem. Most people, give a wrong answer to this question. And as it turns out, it's very surprising that the answer is a very nice, simple answer. Okay, so let's just see what it is. Okay, so you have a group of n persons. Okay, the birthday problem basically asks, what is the chance that some 2 have the same birthday? So at least there are n persons, a lot of people. What is the probability that some 2 of them share the birthday? Okay, so they have the same birthday. All right. So now, if you think of distribution and probability, etc., if you just pick a random person, it's not unreasonable to think that their birthday would be uniformly distributed from 1 to 365. I don't know, in different cultures people get married only at certain times, and they have kids only at certain times. So all these things can affect your uniform distribution, but generally I think it's a reasonable approximation. And can you assume 2 people's birthdays are independent? Yeah, of course. I mean, if you pick them random enough, far enough apart, I guess it's not a bad assumption. So these are reasonable assumptions you can make. So, most people imagine that you should have at least 100 people before you start seeing common birthdays, right? Because uniform independent assumption is probably reasonable. So only when you have a collection of 100 people do you have even a chance of having common birthdays, right? So this is something that's something people naturally assume, but it turns out if you only have 23 persons of this sort, uniform distributed birthdays and independent, then you have more than a 50% chance of 2 people sharing a birthday just with 23 people. Okay, does it sound believable? It seems a little surprising, but it's actually true. You can calculate this probability. So for that reason, let's say event A is that some 2 have same birthday, right? So that's event A. And then let's say event A complement is no 2 have same birthday, right? So in fact, in this problem, it turns out A complement is the easier thing to calculate, right? What is A complement? Once again, how do you calculate probabilities of events? You just write them out one after the other, and then use the AND rule and the OR rule and combine and do it. There's no other way to do it. Okay, so A complement is birthday 1 on any date B1. Okay, for the first person, the first birthday can be on any date B1. I mean, there's no collision if there's only one guy, right? There's no problem. And birthday 2 is on any date other than B1. Okay, so the first person had a birthday on B1. The second person has a birthday, anything is allowed other than B1. What about for the third person? Any date other than B1, B2, and so on and so on and so on till the last person, birthday n, on any day other than B1, B2 to Bn minus 1. Okay, so what's the probability for the first one? Birthday 1 on any date, so that's just 1, right? 365 by 365, everything is okay with you. The next one is any date other than the first guy, so that will be 1 minus 1 by 365, then 1 minus 2 by 365, so on till 1 minus n minus 1 by 365. These are all like condition. You can multiply all of them together, you get probability of A complement. Is that okay? Hopefully convince yourself of this. This is the probability that you will get. Okay. So looks like a pretty long expression. Even for n equals 10, there's lots of multiplication to do, and maybe you can multiply, but I'm going to be a bit lazy. I'm going to write a computer program to do this and verify both by calculation and by Monte Carlo simulation that the probability comes out to be correct. Okay. So here I'm taking 10%, n equals 10, and there's some logic here. First is the logic for calculating the first number I print is the probability from the expression. Okay. So why is this expression that? I mean, you can check that out. I do 1 minus product of 1 minus something that is n by 1 by 365, right. So this is like a short Python code in NumPy for doing this expression. Okay. This is the same expression here that's computed. Okay. And then I have my Monte Carlo. Remember, repetition, experiment, event. Okay. Repetition, experiment, and how I do this is a little bit more complicated. I don't want to go into details of the Python code. Believe me, it's true. This is the birthday problem, and if you simulate, you see you get answers which are very, very close. Okay. So the theoretical calculation that we did and the Monte Carlo experiment that we're doing give you the same value. Okay. So this number by 1000 and the theoretical calculation give you roughly the same value. You can change this number. For instance, if you make this 23, you will get my promised 50%. Okay, so you see the theoretical calculation is 50%. Monte Carlo sure enough gives you 0.523. You can repeat it if you like. So in fact, you may say 50% is still luck, but even if the number goes to something like 40, you literally guaranteed a same birthday. Look at that. That's 90%. Okay, if you have a class of 40 people, 2 people are going to share birthdays with 90% probability nearly. Okay, you have to be really unlucky not to have a common birthday. Even in a class of 40, if you go even to 60, I think quickly this number will go off very close to 100. Look at that, that's 99%. In 60 people, you're virtually guaranteed, right? Unless you're really, really unlucky and really everybody sort of came from very dependent population, it's very, very likely that you would have 2 people sharing a birthday for 60. Okay. So this is just telling you how Monte Carlo sort of agrees with the calculation that's done here. Okay. All right. So that's birthday problem. And the next problem is something called the Monte Hall problem. Okay. So let's look at that next. I have 3 or 4 more problems. I won't probably spend too much time on everything. I'll let you read it up on your own. But this Monte Hall problem is very, very classic. You can read it. This is like a game show. There are 3 doors. Okay, and there's 1 car and 2 goats. Okay, there's a car behind one of the doors. There are 2 goats behind the 2 other doors, and you don't see what's behind the door. Of course, I mean, you're a contestant. You just see the 3 doors, and you have to pick a door at random. Okay, whatever you open, you get, right? For instance, if you got a goat, if you like goat, that's a great gift for you. But most people would like the car, isn't it? So if you're lucky, you'll get the car. So it looks like if nothing else happens, the probability of getting a car is 1/3, isn't it? Right. So 1/3 is the probability that you'll get a car. 2/3 is the probability that you'll get a goat. Just luck of the draw. You try and go off. Now this contest is a little bit different. So you make a choice. Okay. The host will not show you what's behind that door. Okay. He'll open another door, right, which has a goat behind it. Okay. So, right, you pick the door. There's something behind the door. You don't know what it is. Could be car, could be goat. You don't know. But the host is going to show you the door. Open the door, which has a goat behind it. Okay. So definitely, whatever you pick, there will be some door with a goat behind it, right? Where there are 2 goats, and the host is going to open that door and show you, here's a goat. Okay. Now you have the choice of switching. All right. You could either stick to your original door, or you can switch. Okay. So the question is, what should you do? Okay, that is the Monte Hall problem. Should you switch, or should you stick to your original door? Okay. So most people who don't do a detailed calculation will say it doesn't matter. Okay. Most people will say it's 1/3 this way or that way. You either switch or you don't switch. It shouldn't matter. Okay. But the fact that the person opened and showed you a goat apparently ends up having a significant impact on what you should do. And the surprising thing is, If you choose to switch, your probability of winning goes to 2 by 3. Okay, you can do a simple setup, it's not that complicated, but a lot of people have been confused by this. Many people don't believe this. Okay, so it makes sense to do an experiment and verify this. Okay, so that's what I've done here. I put here a little bit of a case where I'm not going to go into details here. You can see I'm doing a car location and fixing the goat 1 location, goat 2 location, and then contestants original choice is again uniform, and then I'm checking if it's a goat or not, and then finally I'm counting if the other closed door is equal to car location. So this is the case of success for switch, right? So if you can check this and you'll get 0.669. Sure enough, the simulation bears out. You can see that even if you didn't believe the theory, by theory you can show this. There's a wiki page, and I've given a link here to a wiki page. You can go there and it'll show you why the 2/3 is justified. There's lots of good reasons for it. And, if you don't believe it, if you like computer simulations more, here you go. You can simulate. You see the answers 2 by 3. Okay, so that's the Monty Hall problem. It's a nice problem. Next is something called a Polya's Earn scheme. I'm going to skip this. Here again, you'll see that it works out okay. And the last experiment I've done is something called a simple random walk or gambler's ruin. Okay, so it's a slightly more complicated experiment than maybe what you're used to. So let's walk through this real quick. A gambler has K units of money, K rupees if you like, K dollars if you like dollars, whatever unit, K units of money, and he's going to a casino to play. Don't ask me where is a casino in India. Goa has lots of casinos, if you didn't know. Anyway, so this is the game he does. If he has any money at all, if he has at least 1 unit of money, he's going to toss a coin. Okay, and if the coin results in heads, the casino will pay him 1 unit. You can imagine the casino has infinite amount of money. It's not going to go bankrupt. It can keep on paying him as much as he wants. If he gets a tails, then he loses his 1 unit. He has to give his 1 unit to the casino. Okay. Now, of course, if he loses all money, he's run out of cash, he's bankrupt, and he stops, right? And if he gets n units of money, okay, he will also stop. So n is like his goal. Once he gets n units of money, he feels rich enough. He thinks he can go buy something with that money, so he stops. Okay. So this is called gambler's ruin problem. In fact, it's a special case of the problem. It's called a simple random walk with 2 absorbing barriers. There's a barrier at 0, there's a barrier at n. Right? He starts at k, he'll keep drifting. Okay, he'll lose some money, gain some money, moving around here, there. If he ever hits 0, he stops. That's an absorbing barrier, as it's called. And if he ever hits n, also he stops. This is also an absorbing barrier. So there are 2 barriers, and the person keeps drifting around. You can imagine, right? So there's a toss of coin going on, and he keeps on moving, and the interesting probability to calculate is this probability of bankruptcy. Okay, probability of bankruptcy is interesting, right? I want to find out if I start with k units of money and if I play this game, what is the probability that I'll go bankrupt, right? Now you can say small p is the probability of heads. Okay, so I'm allowing the coin to be biased. Okay, so most casino games, it's not going to be a coin toss which is fair, right? Most casino games are loaded in favor of the casino. It might be slight loading, but even then it's loaded in favor of the casino, right? So say p is the probability of heads and q is equal to 1 minus p. This is the probability of tails, isn't it? So you can show, I'm not showing the details, actually the calculations are briefly shown below, not in great detail. Probability of bankruptcy, if your coin is fair, is 1 minus k by n. Okay. If it is not fair, then there is a more complicated formula involving q by p. Okay, q by p per k minus q by p per n divided by 1 minus q by p per n. Okay, this is the formula. And how do you derive it? There is a wiki page which has some derivations, but actually it's very simple derivations, not very complicated. Let's say xk is the probability of bankruptcy starting with k units. Okay, the main idea is to condition on the first toss. Okay, you have to condition on the first toss. Okay, now xk is probability of bankruptcy given first toss is head times p plus probability of bankruptcy given first toss is tail times q, right? So first toss could be either heads or tails, right? You either have heads and go bankrupt or tails and go bankrupt, right? So then you do the conditioning, it's just the and or combination, right? So you do the conditioning and you write it out. Now notice, what is this probability of bankruptcy given first toss is head? Now if in the first toss is head, you now have k plus 1. Other than the fact that you have k plus 1, everything else remains the same. So what you have is just xk plus 1, right? So this xk is like this nice little function which takes you from k to the probability of bankruptcy. So you just put xk plus 1 here. Same way with probability of bankruptcy given first toss is tail. When the first toss is tail, you lost one money, you went to k minus 1, you have xk minus 1. Now how do you solve these kind of recursions? You need boundary conditions. Boundary conditions is x0 is equal to 1, right? If you got to 0, then you're definitely bankrupt already. So x0 is 1 and xn is 0, right? If you got to n, then you stopped. Okay, so xn is 0. So if you solve this equation, you'll get this. Okay, so I'm not going to show you how the equation is solved. You can take a look at it, but if you plug it in, you'll see this is a valid solution. Okay, both for the case p equals q equals half and p not equal to q. All right. So there is an expression for probability of bankruptcy. All right. So now I've done a Monte Carlo simulation here. So I put k equals 5, n equals 10, and I'm printing 1 minus k by n. And I'm repeating 1000 times. I start with k5, and then if k is 0, greater than 0 or less than n, right? So this is where I will toss a coin, and if it's heads, my k goes up. If it's tails, my k goes down, and that's how I keep repeating it, right? So if k is 0 when it ends, I increase the number, or if k is n when it ends, I won't increase the number, right? So this is how this works. This is where it is. So some of you who are paying really close attention will know, what if it never hits 0 or n? Okay, you may ask, right? What if it keeps on walking in the middle and never hits 0 or n? It turns out that's not possible. You can prove that. In this case, it will either hit 0 or hit n. Okay, so given the way it works, it's a more complicated proof, but you can prove that. But you can see that 1 minus k by n and this Monte Carlo probability agree, right? So I printed first 1 minus k by n, I got 0.5. This number also sort of agrees. Okay, so this sort of probably gives you a hint on how, for complicated events, also you can do Monte Carlo. The Monte Carlo is so easy to do, you don't need any recursive equation, etc. So in real life, a lot of applications, you will have a very complicated sequence of things happening. And to compute the probability, you just have to write a Monte Carlo, simulate it. And for simulating, the only thing we did was uniform, isn't it? We just wanted a uniform toss. Okay, you got it. Great. Now what about the biased coin, right? What if p is not half, right? Can you do simulations? So I put here something that will simulate a biased coin for you. Okay, so we need a method for tossing a biased coin, right? So far we had only uniform outcome. So I put here biased of p comma m. You put in some value for p, it will toss a biased coin for you m times, and it will give you the answer. All right. So that's what biased of p comma m does. Let's run it, get it into our computer, and then you can run it. So p is 0.25. I'm printing p. And then I'm repeating it 1000 times, the biased coin, I'm counting the number of heads. Sure enough, 0.25 results both in theory and in practice. So biased coin is also something you have. Once you have biased coin, you can repeat the same gambler's ruin experiment with the biased coin 0.45, and you can print the theoretical value and the value that you got from Monte Carlo simulation, and you can see, sure enough, it agrees a lot. Okay. So even if the probability of winning goes down to 0.45, right, which is only a 5% reduction in that one experiment, notice the casino is, likely to win, or you are likely to go to bankruptcy, 75% probability. So let's say we push it to 0.4. Let's see what happens. That's already 89%, 88% probability, right? 0.4. If you go to 0.35, I think this should be really close to 100. You have very little chance of getting out alive. So even 0.35 is a good enough, 15% advantage is good enough literally to wipe you out of all your money in a casino. Okay. So once again, take a look at this Python sheet. It's maybe not every line in the program you will understand, but eventually as you progress in this program, in the BSc, do the other courses, learn Python, you'll see that this is a very useful resource for you to have. And what I have for you beyond this is an activity. Okay, what is this activity? Let's see what the activity is. This is the activity for week 1. There's only one activity for week 1, but hopefully it's complicated enough. It will take time for you. You remember the week 0 activity where you went and created a Google Sites for yourself for this course, and you pulled a data set and described the data set and gave a link to it, etc. Hopefully you did that. Now you have an activity for week 1. Okay, so you go through and understand how the various how to set parameters. You don't have to rewrite the code, just how to set parameters. And like I told you, take a template and repeat the Monte Carlo. Okay, And then what I want you to do is to pick any experiment that interested you, right? So we had so many experiments for which we did calculations of probability. Pick something very simple. If you think it's too complicated to do any changes in the Python program, you can just throw a die and compute some probability of some event, right? So you can do something so easy if you like. Okay, it's up to you. Let me not tell you what you want to do. You could try to do binomial. You can do so many things, right? So whatever you choose, you can try to do, right? And you modify the Monte Carlo to repeat the same thing. So you compute a probability of that event by in theory, right? Print that value and then repeat that same experiment in Monte Carlo and compute or simulate verify by simulation whether the probability value matches. Okay, do that for any experiment of your choice and take your own version of the notebook, add that in the bottom and then put it out on your Google Sites page. Keep everything private, shared only within the organization, don't keep it public, and show it in Google Sites page. Okay, so do that. Create a Colab notebook as well, right? So you create a Colab notebook, copy all these things in, add your own little Python Monte Carlo experiment, right, and verify that the theory matches with the practice of computer simulation. Okay, so that's your activity. Hopefully you enjoy it. Hopefully you've seen a quick recap of all that you learnt in Stats 1. So all of this, the theory at least, is something you've already learnt in Stats 1. Maybe some of it was a bit different, but mostly it's recap. So week 1 is almost entirely recap. From week 2 onwards, we'll push ahead with something new and something maybe you've seen a little bit of the random variables and all that before. So we'll start with all of that and keep proceeding as we go into week 2. Thank you very much.